Hello, welcome to video 10 in Advanced Mathematic Modeling. So you might have realized that I go very fast through the material of these lectures because I'm still covering basic ground of probability theory, and I think that most of you have seen this already, but I would be happy to receive some comments in the forum if this tempo is okay, so at least for the basics, or if this is already too fast or maybe too boring because you have seen this 100 times. Just let me know, so I'm not really sure where we start for you to get new material, new terrain. So so far now we have described the fundamentals of probability distribution, random numbers, and characterization by moments. But now if you want to do exercises with the computers, there's in the practical work, there's two orthogonal tasks, so some applied issues that we have to deal with. So, and one is to go from a PDF. If we have a certain PDF, how can we generate random numbers from this? So the first is, let's we have a PDF of our choice. We have given a probability distribution with some certain properties, p of x. And now I want to simulate random numbers with this, and I have the problem: how can I generate random numbers from this? So maybe you're lucky and you have this built in the library of your random number generator, and I've given you some examples for the random and Gaussian distribution that's built in. But if you have something more different, then we need to find ways how we can generate samples of these random numbers. So this is the sampling problem. So we have to find some methods how to do this. How to generate, we can also call it how to generate a realization of the random numbers. And the other problem, that's an inverse problem. And that's just the other way. Now assume we have given a sample of random numbers. So random numbers. So we have our random numbers. And now we want from these random numbers go back and characterize the distribution. Estimate the distribution, the PDF, and characterize it by its first moments. So that's the problem of estimation. So the parameter estimation is the inverse of the sampling. And so either we try directly to estimate the PDF, the distribution, and then I can calculate the moments from the estimated PDF, or we just try to estimate the moments directly. So let's start with the second problem, the estimation. So we enter the field of data analysis. And so what again is the problem? So we have an experiment. This might be your real chemical, physical, or biological experiment, or it might be your numerical simulation. Whatever. And let's assume they produce data. We treat this data as random number. And so in this data will be then a set of numbers, x1, x2, x3, but it will stop after a certain time, xn. Yeah, so we will get n numbers, n measurements, or n simulated data. And so we call this a sample of size n. In German you would call Stichprobe. And it's clear the larger n, the more random numbers, the more data you get, the better you probably can estimate the distribution. And now the problem is, given sample, data analysis or of this estimation, given a sample of random numbers of size n, estimate the PDF p of x and the first moments. So that's really what we would like to be able to achieve. And so this is the estimation. And so now, how do we estimate the mean value? And so the estimated value, we give this a bar. So this is not this brackets, it's the bar because it's an estimation. And this is a function of our sample. And so you probably all know how to calculate the estimate the mean. So we sum all our random numbers and divide by the random numbers, and then we get this x bar, and that's an estimation of the mean value. So compare this, like the mean value was defined for the distribution as the sum xi pi. Yeah? So when we know the probabilities, then we sum of all possible values of all random numbers, and then we get the expectation. Here we have the different task. We have the random numbers, just sum them all up, and then we obtain the mean value. And so how do we get the variance or the standard deviation? So what's the, so it was for the mean, estimation of the variance. So we calculate the variance. Again, we have the bar here, and as we had before, how we calculate the variance, we take our random numbers, subtract them from the mean, we square, we sum up, and now usually you would think we have to divide again by 1 over n, and that's something here we have to divide by 1 minus over n minus 1. But first let's write it down. When you calculate this sum, then you get an estimation of your variance. Compare the variance was here defined as x minus the expectation squared, and then the expectation. So we have again something similar in the formula. Why do we have here this n minus 1? And we have to divide here by the number of independent variables. But if we have here our sample, basically the sample has n independent variables. But if we subtract already the mean, so that we have one information taken out and we have only n minus 1 independent variables left. So that's why we need to correct here by this n minus 1. Another way one could see it is that usually we should here subtract by the real mean value of our distribution, but we don't know the real value of our distribution. This x bar is just our estimated value of the mean, and also when you, that's also an argument. If you would subtract here the mean value, the precise mean value, then you could use 1 over n. But since it's the estimated value, and then you need to correct, and then you have the term n minus 1. I don't want to enter this too much because this goes to data analysis, this goes to more applied issues. But this for the exercises we very often need this. We have some data, and with this we can calculate mean and variance, and if you take them the square root, we have the standard deviation. So that's how to calculate the first moments, or estimate the first moments. How can we estimate the PDF itself? And in order to estimate the PDF, we need to calculate a histogram, a computer histogram. And this was something somehow when I was student, nobody taught me this, and I had to learn this later when I was starting to analyze data sets, how to make a histogram. And actually making a good histogram is an art in itself. So we want to have here, it's our random number, and we want to have an estimator of our density, and this estimator we call the histogram h of x. And so what we do, so first we need to bin our data. So we have to divide this axis into bins. Bin the data, but actually when I say bin the data, it means we have to bin the axis, and we have to define the width of every bin and the position of every bin. And maybe we do it like that. We have here 1, 2, 3, 4, 5, so that's our numbers. But you it already starts to be interesting. Actually the one is the one in the middle of the interval, to the left or the right, and so on. So you see we start to get subplot problems, and we have to find out what's the width, delta x of this bins, and then we just count 1, 2, 3, 4, and so on. And so we take our data, we take the first random number from our data set, and we see in which bin does it fall. And let's say the first data set first random number would be here, and then we say we put here a small thing. And then maybe the next data is 4 point something, and then we have the data here, and then we have true data there, and suddenly then we start to, depending always where new data is appearing. So like we always, like we remember our data is like x1, x2, x3 until xn. And then we take always the next data, we look into which bin does it fall, and this bin is increased a little bit. And if we do this along for many, if we have a large sample, and then we get here finally a characteristic shape. And this shape, this we call the histogram. This should have something to do with our probability density. And then we say our estimated density is proportional to the histogram value of xi. But then you have to see we have here certain widths of the delta x, so we have to normalize the histogram by this delta xi. Why do we have this? Because like the larger the bin here, the higher the probability that a number appears here. So we have to divide the counts in every bin by the bin size. And then we have here a normalization factor, C, and the C has then to be normalized in such a way that the sum of all these estimated values is 1. So this C is 1 over the sum of all this h of xi divided by delta xi. So now when you estimate or calculate or compute a histogram, yeah, so you either can do it yourself, you can define your bins, you take all your data, you count how many data fall in which bin, you normalize the counts by the bin width, and then normalize the whole the resulting histogram, and then you estimate, in this way you estimate the probability distribution. Or you could use in the computer, for example in MATLAB you have the command hist of x, and this command gives you takes it from the sample size, assumes a certain number of bin, and tries to be clever and have a good number of bins by default. Or you give it, for example, a number 100. This means you say, give me a histogram with 100 bins, and then later you can, so this command will automatically plot this, but I recommend you to go in the help office to see you have many options how to place the bins, and also to not only directly plot it, but give you the bin data directly, which sometimes is also very helpful. But there is a lot of subtleties going in the histogram. So so one problem is that the size of the bins is crucial. So let's assume we choose the bins too small. So here is our axis. We want to have a histogram, and we do this very fine scaled. Yeah. then, and if we don't have enough data for this, then it might happen that we get holes. And so then you don't know, this is the distribution that we deal with. Is this really so twiggling, or is the distribution maybe something like this? And the holes here appear only because we have the bin size too small, and somehow we just missed the value here. So if the bin size is too small, and we will find these holes. Now, if the bin size is too big, let's say, let's make the bin size very big so that we don't find the holes, but then we often get a distribution like this, where we don't have so much information, because we cannot resolve the fine structure here because we average too much with the bins. Here we have the problem, we're not able to resolve the structure. Yeah. And if the bins are too big. So my recommendation then, if you have data and you estimate the probability density, play with the bin size, make histograms of different bin size, and then if you have several of such pictures, and then you see with the increasing bin size what structures start to appear, and from which point you suddenly start to see this artificial holes. This might help. Or you could be more advanced and, for example, take random bin size, variable bin sizes. So, for example, you could say, I know already something. Maybe you did some these histograms, and then you found, there we have a higher chance to have random numbers here in the middle and smaller chance outside. So if we have this knowledge already, then we could say here in the middle we give very fine detail of bins. A bit more outside, we have more rough bins, and here even further outside we have even larger bin width. Yeah, so you design the bin widths according to the structure of the data, and then maybe we are lucky and we find really histogram which looks like this. And so it's really fine resolved here and not so much resolved on the outside. If you do this, you have to be very careful with this normalization here. Because here you have much smaller bins than outside, so you have to always take care that you divide the counts by the bin size, or you get artifacts. And unfortunately there is no best rule. You have to play with this according with every data set and find out which bins are the best way to estimate your distribution. Sometimes we also do log-sized bins. So if we know we can have very large random numbers, and so we start with very small bins and then monotonously increase the bin size when we go further. So maybe here we take a bin size of 1 and 2, 4, 8, 16, 52, 64, and so on. So that's sometimes a way to increase the bin sizes systematically, because sometimes you have very large random numbers, and that's, for example, one way we will deal later with. So sorry, it was a bit longer than the 90 minutes in the videos for today, but at least wanted to give you the techniques to estimate densities and to estimate here mean and variance. So thank you for today.